Today's lecture covers chapters 18 and 19. The two in general should probably be called inorganic chemistry because we're talking about almost everything except the organic chemistry that we're going to be talking about next week. So the chapter 18 is actually titled Representative Metals. It actually should be representative elements because it's going to be covering, if you look at your periodic table, groups 1, 2, 12, 13, 14, 15, 16, 17, and 18. The ones that's not going to be covered in this chapter, but will be covered in the next chapter we'll talk about, are the transition elements, columns number 3 through 11. So the first part, let's review a little bit about periodicity, and then we'll start talking about each one of these individually. The periodicity we use to classify the different elements. And it's always useful when you're talking about periodicity to have a copy of the periodic table available. This right here is a particularly good example because it's all color-coded in terms of the background color on them for the representative metals, which will be groups 1 and 2. The transition or inner transition metals, and those will be 3 through 12. And then the radioactive ones, those are the ones that are open in color. And you'll see that of the first 6 rows, the only one there is really technetium. Other than that, except for the transition metals, and 3 of them in row 6, most of the other ones are all transition elements. Are all radioactive elements. Then you have the metalloids, and those are the ones that's the gallium, the indium, tin, and those in that area, the metalloids. And then the nonmetals, boron over to fluorine, and then down over that way, and including the inert gases. You'll also see that the letter of the element can be either black, blue, or I'm not certain what that other color is. But the solid ones in nature, and we're talking about something at 25 degrees centigrade and 1 atmosphere, and those are in the state that they're in, either solid, liquid for if they're blue, and then gas if they are the other color. So, for example, some of them, the elements do exist, but you can't really have them exposed to water or air or anything. For example, any of the ones in the first column there have to be, like potassium here, have to be stored under mineral oil or kerosene or something in order to prevent oxygen from getting to them because they oxidize so easily. And Lord knows what happens with water. That's a very, very fast reaction. Another thing is dipping a wire into a solution of a salt and then heating it causes emission of a colored flame. And it's going to be what the color of the flame, as you see in this one right here, bright yellow for sodium, is determined by the ionic structure of that particular element. And there's actually a flame testing that is done as part of a laboratory. Zinc is an active transition metal as well. We've already seen that before when we have zinc with the hydrochloric acid in order to, when we were doing the experiments and generating the hydrogen gas. Now, also here you have mercury. Mercury is a liquid under normal circumstances, and if you add HCl, hydrochloric acid, to it, it still stays as 2 separate phases. However, if you have an oxidizing agent like nitric acid present, then you can get the mercury is going to react and form a composite. Tin also, depending upon whether it's tin 2 or tin 4, with tin 2 chloride, you get an ionic solid. If you get tin 4 chloride, you've got a covalently bonded material, and it's a liquid. So it depends not only on the element, but also, especially for the transition metals, what its ionic state is in terms of how it behaves and the properties of the molecules that it's going to form. So let's start talking about the representative metal salts. The first ones are, of course, we're talking about sodium. Now sodium, the preparation is described here using a Downs cell, D-O-W-N-S cell, okay? And what they do is they take sodium chloride salt and they melt it. And then with that melting, they have a cathode and an anode, right? And then what is going to happen is you are going to get liquid metal coming out on one part and chlorine gas coming out on another. Now, this has been around for over 100 years now in terms of the method in which you get pure sodium or pure chlorine. And actually, a lot of it started with a fellow by the name of Herbert Dow, the one who started Dow Chemical Company. And it happened back in 1914 at the start of the World War I. And it wasn't for chlorine, it was for bromine. Bromine, HBr, was also found in salt deposits where you have HCl as well. And so what he did is he developed a system using this type of an approach, but his approach was to solve and get bromine out of it instead. The reason why is because all of the bromine sources prior to that, World War I, were all coming out of Germany. And with the embargoes and problems with starting with World War I, is they wanted to have an American source for that. And Herbert Dow said he was just the guy to do that. And he used the salt deposits from the salt basins underneath Detroit all the way up to a little town in Michigan called Midland. And what he was able to do is he was able to sink brine wells, pump the salt solutions out of there, and as a brine solution, he didn't have to worry about the heat of getting it all into a molten state. He could take the brine and apply his electrolysis portion to that. And so he has the Dow cell that he developed and patented, and he was able to get the bromine, and of course the bromine was in a much smaller concentration than the chlorine, because you had a lot more NaCl than you do HBr. And so he was able to make that material, and he also had the Dow scrubbing bubbles came from the Na, which he combined then with hydroxide to give the caustic for that, and he marketed all these other ones. But it was the start of a good, a long and prosperous company, which is now the largest chemical company in the United States. It wasn't just there. It turns out that those bromine salts are also available here in the Boot Heel of Missouri. And Dow had a plant down there, and it was famous for extracting that. And they had a third one down in Freeport, Texas. So I had an opportunity early on in my career. That was the first chemical company I worked for. Another one that involves electrolysis is the production of aluminum. Now, aluminum is the third most abundant element in the Earth's crust. However, it wasn't until 1886 that Charles Hall was able to finally extract aluminum from the aluminum oxide salt. So the bauxite took way too much energy to try to separate aluminum out from that. And so iron, which was a lot less common, but still is one of the more common ones, you were able to use that more cheaply than aluminum. So finally, aluminum was able to, from that point on, for example, with his process, prior to Hall developing his process in 1886, the price of aluminum was about the same as for pure aluminum, was the same as the price for silver. In other words, it was about $16 a pound, or $1 an ounce. That's why the silver coin at that time was $1. Yeah, 1 ounce of silver was $1. Anyway, but with his process, he was able to immediately drop that price down to $4.86 a pound by 1888, 2 years after he started that. And just a few short years later, it was all the way down to 78 cents a pound, and was able to start being used in a lot of different materials that had not been possible before because aluminum had just been too expensive. They actually had aluminum teacups and service trays and all of that, which were as expensive as the silver ones. So they were considered, prior to Hall's invention, they were considered a good gift as well. Magnesium is produced by the Pigeon process. This is the chemical reduction process used to produce magnesium through the reaction of magnesium oxide, that's MnO, with silicon, right? At about 1,200 degrees centigrade. Now, you'll notice that this is CaO.MgO, okay? This is the ore, this is the calcined dolomite right here, calcined dolomite ore. And so this is the form in which it occurs in nature. So it's always good when going through this part of the chemistry to know, okay, this is the ore for that. Where can I find that ore? Okay. And then, of course, silicon is just used to help with the reaction here. And for this reaction, heating at that temperature, you get the magnesium, which can then be poured into strips and the different things that it is used for. And then you get a calcium oxide silicate type of salt. Okay. So anyway, those were the representative metals. Let's now talk about the metalloids rather than those other ones. Now, the metalloids are the ones that are fall underneath aluminum, like gallium, indium, thallium, tin, lead, bismuth, all in that area. Actually, it's boron, also silicon, germanium, antimony, tellurium. Those are all part of the metalloids as well. And you can see that boron, as it is an isohedron with symmetrical solid shape, 20 separate faces, each with an equilateral triangle. And the faces meet at 12 separate corners for this type of a structure. And the dashed lines means it's going back into the page, and these lines mean that there's coming out from the page. Silicon is used a lot in the semiconductor industry, and the impure silicon, or essentially sand, is heated up to a very high temperature, and you get your molten silicon there, and you can purify it through the temperature refining. And in doing it in such a way, you can have it then so that you can make extremely pure glass out of it, or many other types of glass as well. This right here is boron tetrafluoride, and you can see that it can accept and form an ion with boron tetrafluoride, from trifluoride to tetrafluoride, but this right here is an ionic form. And that sort of thing, boron, you use that to form borosilicates so that they don't heat as much when they're broken. And the inclusion of these borates in the glass helps mediate the effects of thermal expansion and contraction. Okay, so it doesn't have the thermal shock that you would have otherwise. This shows you the symmetry for the boric acid, and then there is this one right here for the borate anions, and how they form up into different types of groups, almost forming an infinite chain there. And we're going to stop right there and start with this slide for the next